Thanks for the introduction, Emmanuel. I just want to start by saying that I'm very excited to be here and talk about my work. What I will do is that, I'm going to present this paper Cosine, like Emmanuel said, part of, like, this is accepted for VLDB 2022, but this is actually part of a bigger project that started off in 2019 about, so basically understanding why designing efficient storage is one of the major bottlenecks for modern data systems, and what we can do to create tailored solutions for any application context. So I would be taking questions both during and after the talk. So, just feel free to interrupt whenever is a good time. I don't also feel free to raise hand, but I'm not sure if I will be able to follow the raise hand, like how many hands are raised. So in case I don't pay attention, just feel free to, interrupt and just ask questions whenever is a good time. Yeah, I want to start off by also saying that there has been some amazing people I have worked with during the course of the project. So I have worked with Meena. Meena is right now a PhD student at UC Berkeley. Wilson is also another PhD student from the lab right now. He is at sabbatical, and Stratos is my advisor. Okay, so with that, I would like to start. So, since the inception of computer science, storage has always been a very critical part of data systems. And this is precisely because storage controls how data is read and written into a system. So basically, every time we are building data systems, how much performance we can extract from a system largely depends on the efficiency of the underlying storage solution. And this, of course, is getting more and more crucial these days because we are building fancy data systems. So paying attention to the design of storage makes sense. Now, we are in this fascinating time where everything around us is kind of changing too fast, right? So we are seeing that there is exponential growth of data, both in terms of volume and velocity. We are seeing super exciting hardware trends with the inception of GPUs or TPUs and persistent memory and so on. Applications are also getting more and more diverse almost every single day. And in fact, our perception of performance has also evolved a lot, right? So classically, maybe we were only interested in a holistic throughput or a holistic, let's say, latency. But now we also care about other kind of metrics, like, let's say, what is the energy efficiency of a system, or what is the tail latency of operations in a system, or how can we add features easily within a system, and so on. So basically, the point here is that the context with which we are building data systems is continuously changing, right? And as data system designers, we somehow have to keep up with this change. Now, of course, today we cannot create a new data system for every single context because, designing and creating data system is something that cannot be done overnight. It takes a lot of effort. It takes a lot of time. So what we do instead is that we take existing systems and we make them adapt to this new context. And this in turn somehow creates suboptimal data system designs. Some of the immediate effects of suboptimal system designs would be either a high cloud cost or low performance, or maybe high energy consumption, or maybe high costs of adaptability, and so on. Now, back in 2019, when we started off with this project, we wanted to get to the source of the problem, like why we do not understand much of this cost performance trade-off. And we figured that the source really is in the fact that designing data systems on cloud is an inherently complex task. So there are so many decisions involved in the process of designing data systems on cloud. So for instance, today, let's say I want to run my own application on cloud. So I have to start off by making several decisions from the get-go. So first thing I will need to decide is, well, who will be the cloud provider for my application? And again, like statistically speaking, about 77% of cloud users, they kind of face this problem of just picking the right provider based on their needs, because there are so many of them out in the market, right? And each of them has their own pricing policies. They have their own hardware offerings. So that's like one level of decision making we have to do. And then once we know who would be the provider, the next decision we have to take is, well, what would be the storage engine design for my application? And now at the core of storage engines are data structures and algorithms. So basically they control what kind of performance the storage engine will optimize, right? So basically if you have a BTree-based storage engine, that is going to optimize more of, let's say, lookups and range queries, but that's not going to be as good for writes. But if you have, let's say, a log structured merge tree-based storage engine, it's a LSM is a write optimized data structure. So then that storage engine is going to be more of, it's going to optimize more for writes. And again, these are like some of the data structures that I'm mentioning because they are the ones that are widely used in industries and academia. But if you look at the space of data structures, you'd see that about dozens of new data structures get published almost every year just in SIGMOD and VLTV, right? So, I mean, this is a much larger space where we could have different other kinds of designs, which could be like extremely, like they could be like very different designs. They could be hybrids of existing ones, or they could be just tunings of existing ones, but they do exist. So that's like another level of decision making. And then while we may think that, okay, cloud provider and hardware is its own decision plane, and then storage engines is its own decision plane. But in practice, we really cannot take any decision about each of these in isolation, because the overall performance we get, that is a function of this holistic combination of cloud provider, hardware, storage engine design, algorithms. So all of them kind of come together, mix and matched, and then they map to performance. And then not to forget that workloads, of course, are getting more and more complex almost every single day. So we not only have like different types of operations, but we could have different proportion of operations. And so this stack then becomes our exhaustive decision space. And the problem really lies in the fact that, firstly, the space is super complex because there are so many layers, and then there are interrelationships among these layers. Secondly, the space is vast. So when we try to enumerate the cardinality of how many combinations are possible within this space, excuse me, we saw that the cardinality can quickly cross more than sextillions of possibilities, which is basically in the order of 10 to the 35. And last but not the least is that today, all of our decisions about each of these layers are almost manual, meaning that we rely a lot on, recommendations or past experience. And you can imagine that given a space that is so vast and complex, any manually made decision is only likely to be suboptimal. And this is something that is a problem for several startups to moderate size industries to large organizations that we see today. So for instance, just to give a quick example here, Viber is it's a calling and messaging application that started, decades back. And at that point of time, it had used MongoDB as its backend server because that was one of the things they thought would work the best. And then over time, MongoDB was not able to scale the way Viber was expecting it to scale. And so in the second generation, they moved to Redis. Redis is basically the backend for, Instagram. And Redis also didn't seem to do that well. And then eventually in the third generation, they have found apparently their best configuration, which is not only using a different design, they're using Couchbase, but they're also deploying Couchbase on half the number of hard servers they were using before. And so you can imagine that this is pretty counterintuitive of what is failing, like to know what is failing. Is it just the design or the hardware or the cloud or the combination? And so this is something where we see that there are plenty of situations where people have moved across designs or across hardware or provider. Now, given this is the problem, if you have to think about what is the ideal solution or what's the dream solution, then it would be as follows. Like if we could create the perfect storage engine for any application context so that the design of the storage engine is specifically tailored to the task at hand, then that would kind of be best. Right. Is there a question? I mean, this is a good point for me to pause anyway.
Are there any questions? Questions?
I have a question. So you mentioned that later you migrate to Redis, right? So compared to MongoDB and Couchbase, so why do you choose Redis to do the experimental then?
Sorry, I was not able to hear it properly. Would you please repeat it again?
Yeah. So I'm just wondering. So why do you choose to migrate to Redis to do the experimental continuously rather than continuously using MongoDB or Couchbase?
Is the question like why did Viber decide to switch the designs?
To Redis. Sorry.
Oh, to Redis. Yeah. So basically, their problem was scalability. And I think this is the problem, generally speaking, for most applications, that they are not able to scale. And when we are not able to scale, then we don't really know what is going on. I mean, if we know, that's good, but it's hard to know. Either the data layout is not, enough, or maybe it's suboptimal, or maybe there are algorithmic issues that we need to fix, or maybe this is a hardware issue and not at all about the design. I guess the point that I was trying to make here is that we don't even know if the shift to Redis made sense, but to them, that was the best they could do at that point. Like they could come up like that was their immediate, like their intuition that moving to Redis might help them with their scalability. And that's why they took the step. But like you were saying, like apparently it seemed that Redis was also not the solution. And then they had to look into into the deeper part of their design and how it interacted with the hardware. And they eventually came up with a completely different design hardware combination, where they even halved the number of servers they were using. Does that roughly answer the question?
Yeah, that makes sense. Thank you.
Cool.
All right. Awesome.
Cool. Okay. So yeah, I mean, this is basically the goal we are looking at. And keeping that goal in mind, and before actually starting off with the solution, I want to take some time explaining what is our take on this problem, or what is kind of the key intuition behind our solution. So the key intuition is as follows. So there is a really large space of all possible storage engine designs that are there. And each of these points are storage engines. And the way you can think about storage engines is that they are nothing, but they are a combination of a set of fundamental principles or low-level decisions, right? So every time you think of a storage engine, it is just some of the decisions coming together and creating an impact so that they become a RocksDB or they become a MongoDB. So each of these points are different storage engines where the combination is different. And all possible storage engine designs that like all the existing ones that we have out there today, they only comprise a very small space of this massive space of possibilities. And we are trying to ask ourselves this question that, well, can we reason about this massive design space of storage engines? And by reasoning, I mean two things. So firstly, I mean, can we know what are these fundamental principles that take part in the design process of a storage engine? That's number one. And then once we know what are these principles, can we somehow know for sure how each of these principles impact our end product, which is, let's say, cloud cost or performance? If we can do both of these, then given any context, let's say a workload or a budget, we should be able to somehow navigate through this space and say that, okay, this is the best combination of fundamental principles, or this is the best storage engine that maximizes my performance goals. That is kind of the overall intuition. And with that intuition in mind, we propose Cosine. Cosine is a self-designing key value storage engine. What it does is that it takes in a workload and a budget as input, and somehow it navigates through this, massive space of possibilities, and then it outputs the storage configuration that optimizes the cost performance balance for the input. And by configuration, I mean whatever combination of storage engine design the hardware on which the design will be deployed, and the cloud provider. Whatever combination optimizes this balance for the input. That's basically the input output of Cosine. So firstly, I would give a little bit of overview on what the workflow and the high level pipeline of Cosine looks like. And then we're going to talk about one or two parts in detail. So at its core, Cosine has this storage engine template. This template is nothing but you can imagine this is a dictionary of design abstractions that allow us to create very structured definitions of arbitrary key-value storage engines that fall within this space. So basically, this template has two parts. It has layout primitives that contain the superset of all possible decisions involved in thinking about different data layouts. And then it has algorithmic abstractions, which is again a superset of all the fundamental decisions involved when we are accessing data. So just to add more concreteness to what I mean, let's say layout primitives. So every time we think about data layout, there are so many design questions that come to our mind, right? So for instance, how much data goes to memory, and then how much data goes to disk? Then even within disk, how do you store your data? Do you kind of store it in a flat log, or do you kind of build a tree out of it so that it's hierarchical in fashion? Or if you have a tree, how many levels the tree should have? What should be the capacity of every level? Then within a level, how do you store your data? Do you always keep it like one sorted thing end to end, or maybe you break it down into different partitions that are sorted, but not like the partitions are not externally sorted, and so on. And then for some storage engines, they also have a way to classify data into hot data and cold data. So the hot data are the ones that are accessed more frequently. And in that case, they have support of special like auxiliary data structures in memory to access the hot data fast. And for that, they could use different types of things like filters, they could use indexes, they could use a block cache, they could use an in-memory buffer. And then obviously the question is, how do we kind of allocate memory across all of these? So then all of these questions can have different answers. And by taking all the answers together for all of these questions, what Cosine does is that it creates this superstructure. The superstructure is nothing but an encapsulation of all possible data layouts within this space. And any data layout does not have to have a value for each of these, but they could have a value for a subset of these, and they would be still valid data layouts. So basically, by setting different values to each of these primitives, we can now start synthesizing the definitions of not only classical layouts like a leveled LSM tree or a tiered LSM tree, or let's say a BTree or a log structured hash table, but we could also start to see the gaps in the primitive space, and we could start synthesizing hybrid layouts. So for instance, in this case, I have shown an example of a hybrid layout where you have LSM-like structure on top for the hot levels, and then for the cold levels, you have a BTree-like structure on bottom. Does this data structure or data layout make sense? I mean, that is a secondary question, and we will visit that. But is this a valid point within the layout space? I mean, yes, it is. So we are able to kind of create structured definitions of these layouts, and we do the same for algorithmic abstractions as well. And together with layouts and algorithms, now we can start, synthesizing full-fledged systems with layouts and algorithms. So now we can start synthesizing not only a classical, let's say, RocksDB or a WiredTiger or a FASTER, but we could also create new data system designs within this primitive space, right? I'll quickly pause to see if there are any questions here.
Does anyone have questions?
Cool.
Or maybe one detailed question. I can see that as a trade-off. Would you, consider like for a given scenario to select like one of those data structures, for instance? Or I guess in some cases it could be possible that, for instance, different tables in the database would be best represented by different data structures within this spectrum, which of course increases the search space. It might not be practical to consider that possibility.
No, I definitely agree with that. I think this is kind of the direction where I am currently working, like I'm extending Cosine for that kind of space where, so in Cosine, it's all about key value space. So we don't have necessarily this idea of tables, but if I extend this thought from what you just said, it could be something like different partitions of data. I mean, it's the same data set, but different partitions of the data can have different kind of data layout. So for one partition, I could have like a BTree layout, and then for other, I could have like a hybrid layout or some other thing based on the workload. And so this definitely makes sense. And what you're saying that it blows up the search space, that is also true. Eventually, we will see that this can blow up the search space to an enormous extent and can kind of make us think how we should revisit this problem, in a sense that there is again a trade-off between how accurately we want to do this, as opposed to what is our search time complexity and when do we want to finish this job.
Okay, yeah, that makes sense.
Yeah.
Are there any other questions? All right, I think for the moment.
Cool. So basically, so far I've only spoken about how we can create definitions using this template of different storage engines. Unless we can evaluate if a definition makes sense for a workload, it means nothing, right? So now, in order to be able to say that if a certain template specification is good or bad for a certain input, Cosine has cost models. And this is where I'm going to spend more time. But for now, you can think that at a high level, these cost models take into account the cost of data movement and concurrency and CPU effects. And it comes up with the estimated latency of running an input workload on a certain hardware configuration. And that's how it says that, okay, if you use this kind of storage engine template for this workload, it is going to cost you X latency. And that's it. And this is a useful metric because now using the cost models, you can not only evaluate different specifications, but you can compare them and you can prune them. You can just figure out what is a better configuration and so on. And once Cosine has this cost models, it uses a search algorithm. What the search algorithm does is that across this whole space, it is going to visit each of these template specifications and use the cost model to ask what is going to be the latency for running workload with this specification. And with that kind of knowledge, it is going to prune out the ones that are redundant or the ones that are suboptimal. And the goal is to eventually build this hyperplane or this performance continuum. It's a Pareto frontier where what we are doing is that along different cloud cost, we are keeping a track of what is the optimal performance that's possible and what is the template configuration that is responsible for that. The reason for this continuum is multifold. So firstly, obviously, given an input budget, we can navigate the continuum and figure out what is my point where what template specification I should use to optimize performance. That's one thing. But then the other thing is also that we could ask what if questions to this continuum. We could say that, well, what if I increase my budget by another $100? And this question is not going to need me to run the search again, because now we have the continuum, and which is it's a dimensionality reduced space. And so basically we can traverse that and we can say that we can explore neighboring configurations and quickly answer to what if questions. That's basically the purpose. And once we are happy with whatever configuration that Cosine suggests, then we move on to the last step of Cosine, where what we do is we materialize the code for that configuration. By materializing, what we mean is, so there's a templated storage engine in Rust that is implemented within Cosine. Based on the template specification, Cosine is going to activate and deactivate different parts of the code, and it is going to generate the code that is ready to be used by the input workload. And this is kind of the end-to-end pipeline of Cosine. I mean, for the interest of time, I will not be able to go through all of these components. So I would stick to the one that's my favorite, which is the cost model part. But I'm happy to, take questions or like hear your opinions about any other things that kind of interest you now or later or whenever. But yeah, I'll again pause now to see if we have more questions.
Can you hear us?
Yeah, I can hear now.
Oh, okay, awesome. Yeah, all right. Does anyone have questions before we discuss the cost model?
I have a question about the cost model, so you might introduce it later. But the cost model, it I guess works well in most cases, but there are some cases where the cost model fails, and it might be the actual value that we get might be different from our estimates. So I was just wondering whether whether you have a way to like for instance, if you think something will work well and you actually deployed it, but actually it's not working well, then do you have like a way to gather feedback and like try to make better choices or
Yeah, that's an excellent question. I guess part of your question directs me to think about adaptability of Cosine as well. That, okay, you start off with a workload and then the cost model gave you something that the workload changed and then now things are not working as before, then what you do. So this is, I want to say that Cosine is right now not adaptable. So what we are doing is that given a workload, we are creating a configuration and relying on the configuration. If that has to change, then again, we have to run the search space and again, find the best configuration and deploy it. One of the major reasons why Cosine is not adaptable at the moment is, so we found out that this is a separate research direction that has its own longer term goals. So for instance, if Cosine has to, so Cosine obviously knows if a certain configuration is not optimal. And what the optimal configuration is, Cosine also knows that. But what it does not know is that if a switch would make sense or not. And in order to be able to reason with that, we need to think about several things. So firstly, what is the overhead of a switch as opposed to what are the benefits of that switch? And when I say switch, I do not necessarily only mean switching between designs. It could be designs, it could be hardware, it could be a cloud provider, but that's I think is a very different space. But it could be between designs and hardware or both. And many a times, what the changes that we see from workloads are not, let's say a workload has intermittent changes. So I should be able to identify that this is an intermittent change as opposed to this is a stable change and take my decisions accordingly. So just to give you a perspective that these are some of the things that we have been thinking about, and it kind of made us think that this needs a more longer term planning of the research and coming up with a careful, like just doing a careful investigation of the problem space and coming up with a solution, which is why we don't have adaptive version of Cosine yet. It is more like we have a workload. Our cost model gives us a sense of what would be, and the search algorithm gives us a sense of what would be the best design, and we go ahead with that. Even in the static deployment scenario, there have been cases where we've seen that a certain model, like model weight, was creating inaccuracy, in which case we had to revisit the model, fix the weight, and keep doing this. So it's more like a to and fro process of model verification and model creation that I'm going to touch upon again when we talk more about the model. But yeah, I mean, that's the high level intuition.
Thank you. Sounds good.
Yeah.
Nice. Does anyone else have a question for the moment? Maybe one clarification question. So did I understand it right that so you're essentially creating the entire Pareto frontier of possibilities?
Yes. So basically, we call this a continuum. What we are doing is that for different budgets, and this continuum is very specific to a workload. Like if a workload changes, the continuum. So for a workload, we make this continuum mapping cost to performance. And so one thing we could do is for the input budget, we could traverse the continuum and say this is the optimal point. And then the other thing we could do is that we could ask what if questions to the continuum and navigate through it, saying that, okay, what if I want a 10% increase in performance? Then what's my point? And that's the advantage, that I don't have to rerun the search.
Okay, okay, makes sense. How expensive is optimization in this scenario? Or that might also be something that you discuss later?
No, I wouldn't. This is part of the search actually. But let me give you an intuition here. So optimization within search is as follows. So right now, Cosine does like a slightly improved version of brute force, which kind of makes us to jump, like create discrete jumps across different designs and ask the cost models of what is the best, what is the performance of that design. And that's how we built the continuum. If we are to think of an advanced search algorithm, so we have made like some progress using, let's say, a learned search algorithm. So what we will do is like, we will use a neural network to learn all the, like the model that we have, like the same model, the network will learn, and then we're going to use some sort of a gradient descent to navigate through the space.
All right.
What we see, like we have not found out a concrete solution as to if we should use that. The reasons are this. So obviously this gives us a more accurate configuration. If you think about, let's say, how memory is allocated. So for instance, memory is a non-integral parameter. It can have different values. And so we get a fine-grained allocation of memory across different things. But what we see is that what kind of improvement we get from this revised configuration is a question, because it might be like a 1% improvement on what we were getting using a brute force, but then we are kind of forced to think that is it all worth it, because then we are creating all these neural networks and we are making the network learn our model, but then we are not getting something that's drastically different than what a brute force would help us get. And so is it worth it? And that was when we kind of didn't think a lot about the learned search until now, because now we are like, the moment you think about adding any design choice or any new primitive within cosine space, the search blows up because it's brute force. And then it kind of again gets us to the same problem that, okay, well, if we are adding, let's say 5 new primitives, then the search is never going to finish it. I mean, it's going to finish, let's say, in days. And that's not what we want. So in that case, it again helps, like it again makes us think that maybe we should start revisiting the learned search space. Right now, with the space that I have explained for this talk, even with this modified brute force, the search finishes in minutes. And it could depend for different workloads and different budget, like how many configurations we can afford, etc. But the search finishes in minute. At some point, if I have time, I'm gonna show you the demonstration of cosine, and that's going to help kind of visualize the problem space in a better way.
Awesome. Okay. Minute zones, very reasonable. Awesome. Okay.
Yeah. Cool. Okay. So yeah, I mean, this is the high level picture of the model, that it takes in a template specification as input, the hardware, any hardware specification for, and the input workload is always there. And then it kind of gives us the estimated latency of running the workload on the specified hardware using this template configuration. And again, this is something we have spoken about, that this model is run once for all the different designs we have in this space. And so that is part of cosine's search algorithm that navigates through the space and gives us whatever is the optimal. Okay. So now zooming into the intrinsics of the model takes into account 2 dominant factors that are consequential to performance. So the first is IO cost, or data movement to and from the disk. And then the cost of concurrency, which says that how much of this data movement can be parallelized because there are physical cores available in a certain hardware. And the way we model this, or our intuition for modeling, is as follows. So we decouple the concurrency logic from the IO logic. And we think about concurrency as a separate layer of abstraction that augments speed up on top of an underlying single-threaded system. So let's say you have a single-threaded system where where the cost or the performance only is because like the cost for overhead of performance only comes from data movement. And then you just suddenly add, n cores to the system, and some of these data movement could now be parallelized. Well, the speed up is not exactly n, but it should be something that we are going to see how we find out. But then that's a speed up, and together we could reason that, okay, this will be the overall latency. And the reason we do this is that it helps us to take into account functionally different parts of hardware, like CPU and storage. And at the same time, it allows us to take into account their collaborative impact on performance. But this is, again, like there's several challenges when we think about this. So one thing is that we're trying to build this unified model, meaning like this one single model that is supposed to work for all these designs and all these workload and hardware configuration. So one definite question that came to our mind was that, well, how are we supposed to design it? Should we go with an analytical model because it's fast? But then that's impossible because this is beyond the scope of human reasoning to just create mathematical models for this whole situation. Alternatively, we could use a learned model, which will be way more accurate, but it is going to be slow because there will be cost for training the model and so on. And most importantly, for a system like Cosine, we don't even have the data to begin the training. Like the amount of data we need to kind of train, which means that mapping of all these workloads with configurations and how that maps to performance, we don't even have that data. So what we did was that we brought in the best of both worlds so that they can coexist together and make the solution more powerful. So the way we do it is that our IO model is analytical, where we kind of come with closed form equations to give us a sense of the data movement for a certain template specification. And once we get the latency coming out of IOs, then we apply a learned model that gives us a speed up factor that we can use to discount some of the latency we got out of the IOs. And then together they make the latency predictions more accurate. To kind of give you an overview on the inside of these models. So let's say for the IO model, the first step of the IO model is the design morphology step, where what we do is that given a certain template specification, we want to figure out the high level data structure class of the design. Like what does this design look like? Is it an LSM-based design or is it a BTree-based design? And the way we do it is that it's possible, like there's certain combinations of primitives that tell us what direction we should go. So for instance, if you don't have Bloom filters, then and you also have data sorted within a level and your fan out is in the multiple of block size, then that points to a BTree-based design. And that is how we could figure out if it's an LSM or an LSH. So there are rules for that. Now, once we know what high level class this is, we also want to know how the exact shape and structure of the design look like. So for instance, even if it's a BTree-based design, by looking at the distribution of, let's say, data, the distribution of workload, like how the writes came in or how the bulk load happened, we could say that if this is more of a balanced B-tree, or is it a B-tree that is right aligned or left aligned given the direction of skew and so on. And also the number of levels, what is the capacity of level and so on. And once we know more about the structure of the data structure that's specified by the template, then the second phase is to be able to leverage this structure to reason about the IO cost of every fundamental key value operation. So let's say, to give an example, let's say you have a look, we are looking at lookups. If it's a B tree, then lookups are always going to go to the end of the B tree. But let's say if it's an LSM tree, then lookups may or may not terminate early. And that also depends on what the distribution of data looks like. So what we do is that we come up with a probabilistic existence of keys at different levels of the tree. And then we start formulating the expected level at which a lookup will terminate for an LSM, or the expected level at which a lookup will terminate for a B tree, which is always till the end. And same for a log structured hash table. And that's how we could kind of see that what is the like IO cost per lookup for each of these design classes. And similarly, we do it for other kinds of operations. And once we have the IO cost of all these operations, then again, like given we know what the workload looks like, we could kind of see the latency coming purely out of IOs. And that becomes our starting point for the concurrency model. Now, for the concurrency model, it's a learned model. What we do is that we rely on this very old and very favorite of ours, the Amdahl's law, that kind of gives us this theoretical speed up a workload can achieve when it's fed with a certain number of cores. So the main idea is as follows. So every program has it has a sequential part and a parallelizable part. And as we add more cores, nothing happens to the sequential part, but it's only the runtime of the parallelizable component that decreases. And keeping that in mind, if we know what is the proportion of parallelizable component or this value, like F, for a certain software or a certain application, then we can say that, okay, this is my theoretical speed up when the program is fed with 5 cores or 7 cores. Now, the thing is that so we need to know this value of F for cosine. But again, we run into the same problem that cosine is not one single design. So it's like multiple designs, and multiple designs essentially means different types of code, right? Like it's a different logic, it's a different algorithm. And so one way to reason about the value of F, if we don't want to learn it for all the different designs, is that we only learn it for drastically different design classes. So for instance, we learn it for one representation of BTree, and we think that that's a fair representation of all BTrees that we have, because ideally what's going to happen is that this F will change slightly for all BTrees based on how they are tuned, but they're not going to change as much. But F for BTrees and LSM trees would be very, very different. So with that logic, what we do is that we break the whole design class into 4 or 5 different design space into 4 or 5 different design classes. And for every class, we learn the value of F for each of the fundamental operation. So for every pair, we are going to learn the value of F. So for instance, lookups on LSM or writes on LSM, lookups on BTrees. That's how we are going to learn. And this learning of this value of F is basically a result of several benchmarking trials that we would do. So for instance, let's say to learn the value, like F for lookups on LSM, I would run or I would basically benchmark the performance by varying the number of base data, the number of lookups, the different types of hardware. So the hardware properties are embedded within my benchmarking experience in terms of what the IOs that are offered, the CPU memory ratio, and so on. The hypothesis here is that as we benchmark for different hardware, the performance will be different. The speed up will also be different. But what is going to stay the same is this value of F, because it's basically the proportion of parallelizable component in the software. So basically, every time I benchmark lookups on LSM, I'm kind of invoking the same branches and sub branches of the software. So this value of F is going to look same, like it's like not same, but similar across different benchmarking trials, over which then I can aggregate, and I can do that for all the different classes. And once we get the value of F for every operations, we could also get it for the workload by just using a weighted average. And then this kind of gives us a sense of how we reason about the speed up, which is fed to as a discount factor to the latency coming from IOs to give us the overall estimate. And then, like I was saying, this is kind of again, zooming out a little bit from the model. This is where the model fits in, that we're going to invoke this for different designs and get, let cosine search figure out what is the best for us. Yeah, do I still have the luxury to stop and check if I can take like few questions before I move to the result part?
Does anyone have questions? All right.
Okay.
I see at the moment looks like everything is clear.
Okay, sounds good. Yeah, I'll do the results and then anyway use the rest of the time to chat and see what you guys think. Okay, so again, like the reason we are zooming out from the model is that we want to go back to the original problem we spoke about, that it is important to create and self-design storage solutions specifically for every single context so that we don't have to use one configuration for another type of job. And so we'll see how we can use Cosine to be able to do that and how the cost models are major enablers for us to be able to do that. So here's an example. Here's basically a result where you see a YCSB workload variant. Along the x-axis, you have different cloud budgets. And then along the y-axis, we are going to show the throughput of different baselines and Cosine. So firstly, we're going to show the throughput for existing systems. If our baselines are RocksDB, WiredTiger, and FASTER. What we do is that for every budget, we get the maximum hardware we can get for that system, and we deploy the default configuration there, and we record performance. What we do for Cosine is that for every budget, we let Cosine run through the space and find what is the optimal. One thing to note here is that with its self-designing property and by able to kind of go through the whole search space, it can give us performance that is up to 2 orders of magnitude better than existing baselines. But what is more important here is that all of these points along Cosine's curve are very different configurations. So for instance, in the first, you see it's a BTree-based storage engine deployed on Azure using up 64 gigs of memory with 4 degrees of parallelism. For the second one, it's an LSM-based design on a different provider. For the third, it's a hybrid design, the one that we spoke about in the introduction, where we saw that these are designs with LSMs on top and BTrees on bottom, and they're using different cloud provider, different degrees of memory, parallelism and memory. And so each of these points are unique configuration. And not just that, 2 or more designs that fall within the same design class can also have very different tunings, right? So for instance, these green points are both hybrid designs, but you will see that exactly how the designs are laid out in terms of their fan out, the greediness in which they merge their data within a level, the amount of memory they are using, that is very different. And so a full-fledged cosine curve somewhat looks like this, where you have different classes of designs and hardware and cloud provider along its whole curve. And we basically repeat kind of this experiment for different type of workloads and different type of distributions beyond and across YCSB to basically generate like these results and see how Cosine could come up with the self-designing properties of Cosine and the ability to co-optimize between designs, hardware, and cloud provider can give us results that are better than existing baselines. Yeah, and basically that's about it. I just want to conclude by saying that Cosine is an ongoing effort in the direction of instance optimized spaces. I mean, it's a project that never ends, which is why I love this project. There's so many things that is always happening in Cosine in terms of adding new data structures, adding support for new kind of algorithms, adding new pricing models, or like we also had in the question in terms of how we can make Cosine adaptive. I just feel like that's a very, very long discussion and an important one. How we can improve its search. So there's like so many things that we can do in Cosine. And right now I've been working on including learned data structures within Cosine. Yeah, I don't want to talk much about it unless you ask me, because I want to pause and see if you guys have more questions or thoughts, and I would be happy to answer that.